Thanks everybody for being here. I'm super excited. My name is Dialid. I'm a mathematician and a developer. I've been working in the financial industry for 10 years, mainly or primarily using Python and C++. And I also work on some open source projects. This is one of them. And yeah, the idea of today is to talk about how and why I built this Python library to show stories about stochastic processes. Let's get started. So, what on earth is a stochastic process? Obviously, we were going to go into the mathematical definition. Sorry, there will be some equations. But before we start, let me establish something. Stochastic processes are all around us. We are familiar with them, and we all have an idea of what they are. A very good idea and a very good intuition. And I want to give you 3 examples. First, COVID. We are all familiar when this started, and every day we will see the counts, the number of cases growing, and that itself it's a counting process, which is a kind of a stochastic process. We can think about this phenomenon in that way. Why? Because there was uncertainty about the number of cases, and we were observing with a certain frequency every day, let's say. Second, the weather forecasting. All of us in our mobile, we have at least one app for weather forecasting, especially here in the UK. So rain, sun, wind, and we plan our lives according to this focus. That also, we can think about this as a stochastic process. And last but not least, and this is very close to my day work, in finance, again, in the news we see stock market going crazy, going up, down, interest rates, inflation. These things we understand, we have a feeling for them, they impact our lives, they impact my mortgage, unfortunately. But what I'm trying to say here is all of these things can be thought as stochastic processes, and we have a feeling for them. However, the mathematical definition, yes, this is it, and it's a bit dry, isn't it? Yes, couple of fancy words there, but most importantly, here we can see it's a family of random variables. Here we have the uncertainty part that we were discussing, and they have an index which can be or is usually interpreted as time. We observe with certain frequency, timely, like weekly, daily, hourly. That's the idea. Let's go to something more concrete. A specific example of stochastic process. This is our Orsten-Uhlenbeck or Vasicek processes. In finance, people like to call it Vasicek. Outside of finance, is more known as Orsten-Uhlenbeck. So let's make things concrete. And please forgive me, I had to put the definition. I'm a mathematician, I'm sorry, I couldn't help. But I need this to make my point. So the definition, as we see it here, doesn't give you a lot of intuition, or none. Yes, we know it's an equation, it has some parameters, theta, mu, and sigma, but it doesn't help me to build an image in my mind of what's this object, or what the parameters mean. So stochastic processes can be hard to explain, just going by the mathematical definition. What can we do about it? This is a communication challenge because the equations are precise but not intuitive. And in many situations, it is intuition what is most important. I have experienced this myself in 2 areas. One, as an educator, when I teach my students about stochastic processes, again, sometimes we want to build intuition first, and then that intuition will help us to get the understanding of the mathematical concept. And second, in finance, when we talk to stakeholders, decision makers, sometimes they don't have the background, and also they don't need and they don't have the time. They need clarity. They need intuition about what we are talking about. So the answer is simulation.
and visualization can help us. So we are going to use some of our favorite packages, NumPy and SciPy for the simulation part, and Matplotlib for the visualization part. The task, or my task now, is to use visualization to get a better understanding of the example that I showed you before, the basis check process. So a reminder of the equation, and this is the last equation you will see, I promise. This is the object, and let's use visualization to understand it. First snippet is this one. So here you see two parts of the snippet. First, the simulation part, it's at the top, and we're using NumPy. And here, at the bottom, the visualization part using Matplotlib. Here I want to stress that the first function, the simulate basis stage process, there are many ways to do it, and that's not the point. So we can change the methodology, but the important thing is that we get one path of the process. The second bit is just here in simulate, we set up the parameters. If this works, we can change the parameters. This code is going to work, and we can produce different results. But interestingly, and this is very important, if I change my mind and I think, oh, I don't want the basis check process anymore, I will need to make changes to this code to have that. So the result of the snippet, this one path of the process. Already I get an idea, okay, this is how it looks like, but because there is uncertainty, well, a single path doesn't tell me much, because the next one is going to be completely different. So let's do more paths. And that's the next slide. And now we are in business here. We start seeing something. The process starts at 110, and then it's going down, and then it's kind of stabilizing here. And that already we are building an image. More paths? Yeah, okay. I think these are 200 paths. So again, we see pattern, but it's getting crowded. Now we have so many paths overlapping that it's not so nice. Can we do better than this? And the answer is yes. Let's add a couple of elements. First, the blue line here is an expectation line. So at every step of the process, I'm taking the average here, and this is telling me where the process is going as a whole. And like, yes, there is noise, let's say, or uncertainty, but overall, this is the trend. So this is telling me something. Second, and I think it's not quite clear here because of the light, but there is a probability envelope. So below the paths, there is an envelope, it's gray. And this tells me where the process is going to be most likely. So that tells me, again, something about this process. First, it tells me that it's not likely that this is going to go to 200 or to 0 or 50. It's going to stay in that place. And last but not least, I changed the color of the paths. And now, because usually we care about the focus, the last point. So I'm coloring the paths according to where the last point is. So you can see it goes from blue to red, and you see some of the plots. So there are like some symmetry. We can see some symmetry here. There are as many paths above the central tendency as below, and that's something already that's interesting. It gives me intuition. So next bit is we add a last element, which is this subplot here. So now I'm taking the last point of each path, and I do the histogram here. So basically, I'm counting how many paths end up at this level, and so on. And I do the frequency there. And because this process is kind of nice, I know the density. And if you look at this, it looks like a Gaussian normal. It is. So I'm ready. This is building in my mind a lot of insight about the process. And this is the graph. So let's use these kind of plots to understand my process, the equation. So the mu parameter, so what I'm doing here is constructing the same kind of plot. Parameters are the same except for mu. So mu is 120 and here is 100. Immediately you see that the shape changes. This is growing and this is going down. So this is telling me where the process is going. Mu controls that. It's the long-term mean, and we can see it clearly in these pictures. But because the other parameters are the same, if you look at the terminal distribution, this and that, they look quite similar, and they are indeed quite similar. It's kind of shifted, one and the other, but they look quite similar. So we know here from this plot, we can see that mu is just that long-term mean of the process. Where is it going in the long term? Same experiment, but for sigma parameter, and now the plots look quite different. One is quite wide, and the other quite narrow. Why? Because here sigma is 2.5, and here is sigma is 0.25. So it's the sigma is the dispersion, is telling me how much uncertainty is around the process, like at each step. It tells me the variability of the process. And it also tells me something about the focus, right? The last part. This is quite wide, and this is quite narrow. So even though the mean, you see both processes are going to the level 100, both of them end up in the same place. But this focus is much wider. There is more uncertainty. So if I had to bet, I will bet on this one. Finally, the speed. The theta parameter, we do exactly the same. And here, again, the plots look quite different. And we see immediately that, again, both processes are going to the 100 because it's a long-term mean. But one of them goes super fast because here theta is 1 and here theta is 0.1. So theta is the speed, how fast convergence is happening. And this is going super fast. At time t, I'm already there, while here it takes up to time 30. And again, the focus, the last bit, also changes. So with these plots, I have already built in my mind an idea of what the process is, what the parameters are, how it behaves, how does it look like. Next, we can do the same for other processes, not just for the VASICheck process. And that was the idea behind introducing aleatory, a Python library to simulate and visualize stochastic processes. Aleatory comes from Latin and it means random. The purpose of the library is to do this kind of experiment, like what we did today, explore stochastic processors, help with communication for both education and use in the industry. When we want to communicate something about the process without going into the equations. The design, it's an object-oriented design. Each process is going to be a class. Currently, there are more than 25 stochastic processes supported. The idea was that the API has to be quite simple. The user does not need to know the details of the simulation. So as I mentioned at the beginning, there are many ways to do simulation and different processes will require different methods, but the user doesn't need to know anything about that. And it leverages Matplotlib features, so the syntax we are already familiar with, we can use it. This is like a standard recipe for aleatory, how we use it. This is a snippet. We can see here, this is for the basis export process. We import the process. The second line is just about the style. It takes care of the style as well. Labels, axes, all that is taken care of. And then here, I'm creating the instance of the process. So you can say P equal to your favorite process that is supported. And then the method draw p.draw, n how many steps, capital N how many paths, and then here, as I mentioned, you can use the same syntax that you are used to in Matplotlib for the figure size and for the color map that is used over there. And then we show the figure, and that's it. And we can create these kind of plots. So these are some examples that you can produce in the same way, using the same kind of recipe with aleatory. One is the Brownian bridge. Obviously here there is no terminal distribution because by definition this process ends or finishes on a point, which is that one. So that's why, but the other elements are still there, the trend and the envelope. This is a constant elasticity variance process. This is interesting because the equation, the solution to the equation is not explicit, but that doesn't matter. We still can do this kind of exploration and we still get the intuition about the process. This is a Poisson process, which is different because it's not a diffusion, it's jumpy. So it's basically jumping, counting something like the count of the cases in the COVID case. And yeah, so and the last one is a 2D process, so it's slightly different, but again, the syntax will be the same, quite simple and straightforward. So some final thoughts about this. Yes, stochastic processes are powerful mathematical objects, but they don't have to be intimidating. And with the right tools, with Python, we can tell stories about them, and aleatory is here to help you. Thank you so much.
Thank you, Dialid. And now's the time for questions.
Hiya, I really liked your talk.
Thank you.
If someone wanted to do some modeling,
Yes.
how would they know which stochastic process to choose, and how would you help advise people on gaining intuition on that?
Yeah, that's a very good question. Let me see if I can share this. So we have a gallery here that shows you some of the process that you can produce. So first, you have to understand your problem, your process. Think about what it means. Like in the case of COVID, okay, it's discrete, it's counting cases, so it's not going to be a diffusion. That tells you something already. What kind of jump process can you choose? Well, that will depend on more features of your problem. But in general, I think visualization can be quite helpful because it already gives you something. For instance, these are square vessel processes, of course. So these ones, they are positive by definition. So if your phenomenon takes negative value, well, it's a no-no, and so on. So I think it can help you to get this, like look at the pictures, build intuition, and then when you are looking at the problem, think about what your problem needs, and then you will find which is best. And obviously, trial and error. Thank you.
Thank you for the talk and for the library. My question is, if I have a stochastic process that is not one of the ones that is listed, and essentially I can produce the data for the process and for multiple runs of the process,
Yes.
can I use aleatory to plot it? So can the plotting functionality of aleatory be separated from?
Yes,
from those?
there is. So some of the functions, the plotters are exposed. So you can just call the plotters as they own. So you have to pass your paths that you already generated, and if you have some of the plots require more information. For instance, for the densities, the subplots, you need to know something. If you don't pass it, that's okay. It will come without the density, but you will still be able to see something. So yeah, the plotters are exposed.
Do you have any recommendations for visualizing stochastic processes that output two-dimensional data?
That's a very good question. Actually, yeah, I'm working on that because that was obviously like the next question. Okay, what about multidimensional, right? How can we do this? So that's the next step for aleatory to support 2D. I started with the ones that I show, which are these ones, like that one. That's just a 2D random walk, but obviously that doesn't help quite as much. So yes, I'm working on it. The first idea was to extend aleatory to have like a kind of the marginals on the side, so it will be like this, but with two subplots. But obviously you have to think about not to put too many, because when a plot gets like too crowded, we tend to lose focus as well. And again, if you want to communicate this, you want the person to be able to focus their attention on something. So I'm still working on it, but yes, that's a great question. Thank you.
Thank you.
Yeah, so this is perhaps less of a question about aleatory, because and more just a question about general design of visualizations. Is there a particular reason why in your color map you frequently choose white somewhere in there? Because some of it is just, some of the paths are just invisible, right? Maybe not in, yeah, even on the top right one, right? That has a whole bunch of white in there.
That one?
Yeah.
Oh yes, so the color map, you mean?
Yeah, I presume like it's just a choice of color map, so it
Yes.
just has nothing to do with aleatory.
Yes.
I'm just wondering if that's a deliberate choice in terms of communicating visual information, or if that's just a
No.
a choice. Okay.
Yeah, just is the color map.
Okay.
Thank you. Just a quick one then. I was wondering if you've got any sort of guide that walks you through on the page, rather than just like a gallery. What about question by question to pinpoint what kind of process you might be dealing with?
Yes,
Good.
it is quite, the documentation is quite extensive. So if you go to the class of each class, you will see the equation, some extra information about how the simulation was done. So yes, there is documentation for all the processes that are supported.
That's great. Do you think an LLM might be able to digest that and help guide, or do you think it's, speaking of non-deterministic processes, do you think it would hallucinate a lot there, or do you think it might? Depends on the thing, doesn't it?
Yes. I mean, we need to try, I guess, yeah, because you never know with LLMs.
Thanks for the talk, really fascinating. This is an audience of, I presume, mostly, if not all, engineers. And we, like, inherently understand graphs,
Yes.
color maps. I was wondering if this has helped you explain some of these processes to non-technical people as well. And yeah, could you talk through that?
Yes, for sure. Especially when, for instance, actually the basis check process, it has the mean reversion phenomenon. And usually we use a lot of mean reversion stochastic processes, and we want to explain, and sometimes we show like actual data for, like, let's say, all prices, and we see, okay, we try to explain that to stakeholders and say, okay, this is what you see in the market, and this is what we mean by mean reversion. But then we show our model, and the model is like, these equations, and I'm trying to convince them that my model does or reproduce the phenomenon that they see in real life. So I show them a bunch of simulations until I convince them that my model works.
Thank you, Dialid.
Thank you so much.